One very useful result that comes out of the field of dimensional analysis is something called the Buckingham Pi theorem. The Buckingham Pi theorem says that any relationship between n quantities representing m base dimensions, where the n quantities are not dimensionless quantities, can be written using p dimensionless quantities, which we call pi 1, pi 2 through pi p, where the number p is n, the number of dimensional quantities, minus m, the number of base dimensions represented in those quantities. What this means is if we have a function of n independent variables, we can rewrite that function as a function g of only p variables, where p is always less than n. Here's a simple example to illustrate how the Buckingham Pi theorem predicts the dimensionless model equation. Consider a chemical reaction occurring in a fluid stream flowing through a tubular reactor. The chemical reaction is a first-order decomposition of component A, described by a rate law, R equals minus K times the concentration of A. We can write a component A balance equation describing how the concentration of A changes as the fluid flows down the length of the reactor. If we consider an Eulerian control volume representing a slice in the middle of the reactor, and we write a balance equation for component A, and then we shrink that control volume in the z dimension to an infinitesimally small length, we can derive the differential equation describing how Ca changes as a function of length down the reactor. Since this is a first-order differential equation, we need a single boundary condition to solve it. We'll set Ca equal to Ca0 at the entrance to the reactor where z equals 0. Then we can solve the equation to predict the concentration of A at any point z down the length of the reactor. It's equal to the initial concentration times e to the minus kz divided by v sub z, where k is the rate coefficient for the first-order decomposition of A, z is the position down the length of the reactor, and v sub z is the z component of the fluid velocity. This model equation contains the number e and 5 other dimensional quantities, Ca, Ca0, k, z, and v sub z. These 5 dimensional quantities contain only 3 base dimensions: moles of A, length, and time. Therefore, according to the Buckingham Pi theorem, we should be able to write this expression using only 2 dimensionless quantities. We can derive those dimensionless quantities by dividing the equation by Ca0 and defining a dimensionless concentration chi A, which is Ca divided by Ca0. The argument of the exponent is already a dimensionless group, which we call zeta. Zeta is what we call a type 1 Damkohler number. It's a characteristic reaction rate divided by a characteristic transport rate. Many of the dimensionless groups that appear when analyzing chemical and biological processes are so common that they have names, and you'll become familiar with these names as you encounter them in later classes. This expression is simpler than this expression because it contains far fewer variables. Only 2-dimensional variables instead of 5-dimensional variables. In this example, we derived the dimensionless quantities from the model equation itself. The Buckingham Pi theorem can also be used to derive dimensionless quantities when we don't even have a model equation. This is very useful for developing empirical models because it can reduce the number of variables required in the model and therefore simplify the model. To do this, we simply make a list of variables that we think should appear in our model equations, and then we choose m of those variables as a recurring set. Remember, m is the number of base dimensions. The recurring set should comprise a complete set of dimensions. That is, we should not be able to form any dimensionless variable by combination of the m variables. We'll show one way that we can select these m variables by an example. Then we write each of the base dimensions, length, mass, time, temperature, energy, moles, whatever appears in our model variables, in terms of the recurring variables. And then we use the m recurring variables to de-dimensionalize the remaining p non-recurring variables. Those de-dimensionalized variables become our pi variables. As an example, let's consider the heat transfer between a fluid and a surface. We think that this heat transfer should be described by an equation. The rate of heat transfer is equal to some heat transfer coefficient times the difference in temperature between the fluid and the surface. The trick here is to model this relationship, instead of using a heat transfer coefficient, using parameters that describe the system, like fluid properties and surface properties. So that heat transfer coefficient probably depends on lots of properties of the system and the fluid. We want to rewrite this model equation as the heat transfer rate, instead of being proportional to h times delta T, we want to write it as a function of the properties of the system. These might include things like the thermal conductivity of the fluid. Of course, the delta T will appear, the fluid velocity, maybe some length scale associated with the heat transfer or associated with the dimensions of the surface, the density of the fluid, the viscosity of the fluid, the heat capacity of the fluid, and a parameter beta G that might describe free convection. It will probably be very difficult to derive this relationship from first principles because it contains so many possible phenomena. Furthermore, it would be extremely difficult to conduct experiments to derive an empirical relationship because we have a 9-variable parameter space to explore. And even if we use very simple relationships like lines and polynomials to represent the effects of each of these parameters, we're still going to have a lot of coefficients in our model if all of these parameters are included. So instead, we'll choose a basis set of recurring variables. Now, our basis set of recurring variables only needs to contain 4 variables because there are only 4 base dimensions represented among the variables shown here. Those base dimensions are length, mass, time, and temperature. To choose our recurring set, we'll try to introduce one new dimension with each variable. This will help us ensure that we have a complete set. We can begin with the length dimension because we have a variable L that only contains the length dimension. Next, let's try to introduce mass. We don't have a variable that represents a mass, but we could use the density, and that introduces only one new base dimension to our basis set. We've already got length, so by introducing density, we introduce mass without complicating things. Next, let's introduce the time dimension. Again, we don't have a variable representing time, but we have several variables that contain mass, length, and time. Here, we'll choose the viscosity. That introduces the time dimension without introducing any other dimensions. Finally, we need to introduce the temperature dimension. It's easiest to select delta T to introduce the temperature dimension because delta T is temperature. By selecting them in this order, adding one base dimension per variable, we ensure that our recurring set is a complete set. And we cannot form any dimensionless quantities by combination of just these 4 variables. Next, we write the base dimensions in terms of these variables in our recurring set. So we need a combination of these that will give us length, mass, time, and temperature. Length and temperature are easy. To get mass, we just need to multiply the density by L cubed. To get time, we divide rho L squared by mu, and temperature is already done. Next, we'll de-dimensionalize the remaining P variables, H, K, V, Cp, and beta G, using the quantities here that represent length, mass, time, and temperature. The quantities representing length, mass, time, and temperature, containing only our recurring set, are written here on the left-hand side. We'll start by de-dimensionalizing H. To de-dimensionalize the heat transfer coefficient, we need to multiply by length squared, time cubed, reciprocal mass, and temperature. We do that by selecting these quantities here, and then after some simplification, we arrive at our first pi variable, which we call pi 1. Next, we de-dimensionalize the thermal conductivity. Again, to de-dimensionalize thermal conductivity, we need to multiply by reciprocal length, time cubed, reciprocal mass, and temperature. And so we select the quantities here that will achieve that de-dimensionalization. After some simplification, we arrive at this group for our second dimensionless variable pi2. When de-dimensionalizing the velocity, we need to multiply by time and divide by length, as done here. You might recognize this as the Reynolds number, which you'll see in CBE 331. Doing the same thing for the heat capacity and beta g, we find the last two pi variables. Pi 5 is something called the Grashof number. In fact, all of these pi variables can be represented by familiar groups of dimensionless variables, such as the Nusselt number, the Brinkmann number, and the Prandtl number. The Reynolds number is a ratio of inertial forces to viscous forces in a fluid. The Prandtl number is a ratio of two diffusion rates, the diffusion of momentum and the diffusion of thermal energy. The Nusselt number is a ratio of two heat transport rates, the convective transport rate and the conductive transport rate. The Grashof number is the ratio of buoyant to viscous forces, and the Rayleigh number is the product of the Grashof and Prandtl numbers. The Brinkmann number is a ratio of the conversion of mechanical energy to thermal energy by viscous dissipation to the energy transported by conduction. Now, instead of writing Q as a function of these other variables, we can write pi 1, or the heat transfer coefficient, as a much simpler function of just four other dimensionless variables. That is, we might say the Nusselt number is a function of the Reynolds number, Brinkmann number, Prandtl number, and Grashof number. This does not tell us how the variables are related, that is, what the functional form of either G1 or G2 is. In fact, this depends on many other details of the system, but it does give us a starting point for developing dimensionless empirical models that contain far fewer parameters than our original dimensional model. In fact, there are many empirical models that predict Nusselt number as a function of some subset of these other dimensionless numbers for lots of different situations. For example, for free convection near a vertical wall, when the Rayleigh number is less than 10 to the 9th, the Nusselt number can be predicted by this mixed power law containing just the Rayleigh and Prandtl numbers. For laminar flow of a fluid over a flat plate at a position x from the edge of the plate, the Nusselt number is predicted by this power law relating the Nusselt number to the Reynolds number and Prandtl number. Because heat transfer from piping systems is very important in things like heat exchangers and chemical reactors, there are lots of different correlations used for forced convection in pipes. For example, the Dietz-Boelter equation relates the Nusselt number based on pipe diameter to a Reynolds number and a Prandtl number. Empirical models formulated as power laws like this are extremely common in chemical and biological engineering. In the next video, we'll talk about another very useful application of dimensionless quantities, which is in scaling models of chemical and biological processes.